How well do you know yourself? That's the question I want you to keep in the back of your head for the next 18 minutes. Now, behind me on the screen, you'll see a scanning electron micrograph of a human chromosome. You're actually looking at molecules, and these molecules contain the information to create, grow, and maintain a human being. Now, genomic medicine, the topic of this talk, seeks to leverage that information to extend and improve life. Now, this is a big deal. This is going to affect each one of us individually, and it's going to affect our society, our cultural value system, and probably our economy as well. So, for your consideration, I would like to give you some information about genomic medicine, a few example applications of genomic medicine, and perhaps a way that we might be able to more broadly implement genomic medicine in the population. But first, we have to understand the genome. So what is the genome really? It's the plan. Now, it's often been analogized as a book. The chapters, paragraphs, sentences, words, and letters of the book forming the story, and you are that story. It's been analogized as a blueprint, and you are the building. And quite beautifully, it's been analogized as a musical score, and you are the music. I think it's time to put these analogies aside and learn about the genome directly in a way that is helpful and useful to us as we move forward together. If I asked you, what is a heart? Define it for me right now. You would say, yeah, okay. Heart's a muscular organ about this big, lives in my chest right about here, got 4 chambers connected to the circulatory system, pumps blood. If I were to ask you, what is a gene? Could you define it? Well, the truth is that we use analogy because genomics is a little bit complex. But the truth is that I think that you have the ability to understand this information, and I encourage you to try to learn about it directly. So, generally speaking, the genome is a set of large molecules, DNA, and information is stored in the chemical structure of these molecules as patterns. Now, it's organized into 23 pairs of chromosomes, very grossly. Half of the pairs come from your mom, the other half comes from your dad, and every single cell in your body has a complete set of the genome to create a whole human being. Further, the chemical structure part of the genome is it's made up of nucleotides, 3.3 billion nucleotides, and they're represented on the screen behind me as finger-like structures protruding inward from the helical backbone as A's, C's, G's, and T's. Now these A's, G's, G's, and T's, they come in functional units, and these functional units are called genes. If you get nothing else from this talk today, take this away. Genes code for proteins. That's it. That's all they do. It's an instruction for a protein. And you, me, all of us, we are made of protein, right? So genomic medicine concerns itself with the order and organization of these A's, C's, G's, and T's. Indeed, sequencing is just that, to learn what is the order of these things, right? That's all it is. Now, we share a common set of instructions to make us. But there's tiny variations in the order and organization of these A's, C's, T's, and G's. I mean, if you look around you, you will not find one person that looks like you, sounds like you, smells like you, whose body functions like you. And these differences, this variation in A's, C's, G's, and T's produces all the differences in the humans we see. And every single time we reproduce ourselves, we create 60 to 70 new variants. Now, most of the time this is totally benign, but we're finding that even a single variation in a critical part of the genome can have a profound impact. In this case, a single change causes severe intellectual disability. Medicine. Now, medicine today is practiced by guideline. What does that mean? Well, if you're 40 years old and a man and you go to the doctor, you're going to get a prostate exam. And if you're 40 years old and you're a woman and you go to the doctor, you're going to get scheduled for a mammography. And at 50 years old, we get to have colonoscopy, right? But personalized medicine kind of changes the order of that. It's not by guideline. It's medical practice based on your specific needs of your body. And genomic medicine actually forms the largest component of personalized medicine, and it's these order and organization of the A's, C's, G's, and T's. And so what I'm going to do now is go through a few different applications of genomic medicine, and from general practice all the way through idiopathic disease. It's important to understand, though, that the genome sequencing is a universal genetic test, and the real promise of genomic medicine relies on genome sequencing. Your genome, the order of those A's, C's, G's, and T's are fixed at fertilization. They're set. And from that moment to your last breath, they're not going to change. So we sequence the genome one time, and we refer to that data set over and over and over throughout your lifetime to help improve the quality of medicine. So when you go to the doctor, one of the first things they do is take your blood pressure, right? So what do? They take a balloon, they wrap it around your arm, they pump it up full of air, they constrict the blood flow to your lower extremity, they put a stethoscope on your arteries, and they listen as they let the air back out for when the blood begins to flow back into your arm, and they look at a pressure gauge. Well, that's great, but that's reactive medicine. In other words, they're telling you what you have, whether or not you have high blood pressure, not whether or not you're going to get high blood pressure. Now, I use this as an example because genomic medicine can give you predictive qualities. Now, behind me, this is a rather complicated chart, and it's only important that you take away that those symbols in red, those are variants that have been associated with high blood pressure and getting high blood pressure, right? So there's a genomic architecture that we can know and test in advance. In fact, I've had this done for myself, and we can summarize the results of those 29 variants as a simple chart of relative risk. So I have a relative risk of 1, which means that I have about the same chance of getting high blood pressure as other people of my ancestry. We can even extend this to look at what my lifetime risk will be, and that's about 55% chance. But we can do this for much more than just high blood pressure. We can do it for lots of different diseases like prostate cancer. And this is, again, my risk for prostate cancer, which is slightly less than other people of my ancestry. But it's not the same for everybody. In fact, Jeffrey Gulcher, this is his result for prostate cancer. He's a world-renowned clinical medical genomicist, and he has twice the background risk for getting prostate cancer. So Jeff, 48 years old, went to his doctor, and he said, "Doc, I got increased risk of prostate cancer. Would you give me a PSA test, a prostate-specific antigen test, a blood test?" And the doctor said, "Well, Jeff, you're 48 years old. We've been checking your prostate. There's no swelling. Everything's fine. You're fine. And we don't do PSA tests until you're 50. But Jeff prevailed upon his doctor, got the PSA test. In fact, his PSA was high. He biopsied his prostate, and Jeff indeed had prostate cancer. Took the prostate out. In fact, he had a very aggressive form of prostate cancer that would have killed him. In this case, he was able to get that done 2 years before he would have had his first PSA test. That's just an example. Surgical decision support. This is something that's becoming more and more relevant, where genomics can help inform the surgeon. The surgeon at some point needs to answer the question, will surgery prevent or cure some disease? An example that's common right now is breast cancer. That's the BRCA1 and 2. Thanks. BRCA1 and 2 for breast cancer. And these are breast cancer risk genes. And if you have certain variants of these BRCA1 and 2 genes, you have a highly increased risk of getting breast and ovarian cancer. So you can elect, a female can elect to have her breasts and ovaries removed prophylactically to prevent breast and ovarian cancer. Okay, pharmacogenomics. This is another example of genomic medicine, which I absolutely love, and I can't believe that this is not practiced more broadly. Have you ever known somebody who didn't respond to a drug? Right? Okay? That's because all of us metabolize drugs differently, and there are markers in our genome that can indicate whether or not a specific drug works for me as an individual. So how much do we know about this? Well, right now, there are 145 drugs currently sold in the United States that have pharmacogenomic variants associated with them. Raise your hand if you've been tested for a genetic variant before you were prescribed a drug. Okay, so I can't talk about all of these, but I can talk about this one, Plavix. It's the poster child for pharmacogenomics. Now, Plavix is a good drug, really good drug. Helps millions of people prevent heart attack and stroke. We like it. In fact, it's the second most prescribed drug in the nation. But it's just not a good drug for everybody. In fact, 15% of the people that are prescribed Plavix can't metabolize it at all. They cannot change the prodrug into the active drug form. What's more, it's known what variant can indicate whether you can metabolize this, CYP2C19. And the FDA knows this variant as well. In fact, they put a black box warning on the Plavix container. And what it says is, warning, diminished effectiveness for poor metabolizers. So black box warning, it's the same thing that goes on a carton of cigarettes. It says, warning, if you smoke this, you're going to get sick and die. Right? So it says right in this warning what to test for, what to do. And nobody does the testing. Well, Plavix sells about $6.5 billion a year in this country. 15% of the people can't metabolize it. They derive no benefit from it whatsoever. That's $975 million a year wasted for one drug in one country in 1 year. We got some healthcare problems? Maybe we should start here. Okay, and this is an application of genomic medicine that's really relevant to a lot of people and gaining in popularity, and that is family planning, in vitro fertilization, and pre-implantation genetic diagnosis. This is a human embryo about 3 days old, and we are able to now screen this embryo for serious genetic defect at this stage before it's implanted into the woman for pregnancy. So, if you're going through IVF, one of these cells can be removed from the embryo, doing no damage to the embryo, can be screened for serious disease, right? But wouldn't it be great if we could actually have preventive medicine and the impact of genomic medicine from the first breath rather than waiting till we're adults? Meet Nick Volker. Nick is a really, really brave young boy who lives directly across the lake in Milwaukee. And he has idiopathic disease. In other words, he had a disease of unknown cause. Have you ever known somebody that was sick and nobody could figure out why? Idiopathic. So he was normal until he was about age 2 when fistula began to form. And those are holes that formed between his rectum and the outside of his body. Feces leaked through these holes and made him sick. Got high fevers, became septic, almost died many times. In fact, by the time Nick was 4 years old, as they tried to correct these problems, he'd spent more than 300 nights in the hospital. He'd gone through more than, I couldn't believe this, but this is true, more than 100 general anesthesia surgical procedures. He'd had his colon resected and then completely removed. They inserted a G-tube, so all food and drink went through a G-tube. And he'd exceeded his lifetime medical benefit of $2 million by the time he was 4. Fortunately, he had a great medical team, famous case. They sequenced his genome, and they found a mutation in a protein called XIAP. And they reckoned if we do a bone marrow transplant, which was not obvious and it was risky, that we would be able to cure his illness. And indeed, that's what happened. This is Nick in a more recent photograph. So if it's so obvious that we should be sequencing genomes and performing genomic medicine more broadly in the population, why isn't it done? Well, it's hard, right? So the Human Genome Project was kicked off in 1989, and it took us 14 years to sequence one single genome. 14 years. $2.3 billion, hundreds, thousands of scientists working simultaneously, one genome. By 2007, we'd managed to sequence 2 genomes. By 2009, the whole world, in all of human history, had sequenced 9 genomes. Now, with the advent of better technologies, we're getting much better at this, and now I estimate by the end of this year, we will have sequenced about 100,000 high-coverage human genomes, and the cost will have dropped from $2.3 billion for the first one to about $3,000 a piece now. That's a 750,000-fold decrease in price. And it's going to go down more, so it can be used in medicine to about $1,000 or less. So 100,000 genomes is great, but there's 7 billion people on the planet, right? It's just a tiny fraction that we've done, and everyone should be able to enjoy the benefits of genomic medicine. And maybe this is a lofty goal, but I say we try, right? And so here's what I suggest, that we industrialize the process. Now, every person in this room has a mobile phone, and that's because we've industrialized the process to make them. Most people have cars. We industrialize the process. Let's do the same for the genome. And that's an issue of logistics, right? We're all distributed. So the first step in industrialization is to centralize the biological samples in biobanks. Now, this is the biobank from Iceland, which has about 200 and some thousand blood samples in it from the entire country of Iceland. This is the biobank from the UK. These things can then go into a factory-based sequencing facility to generate lots and lots of genomic data, which can be uploaded then to large server-based cloud systems and distributed back out to wherever the information is needed. So I've been getting National Geographic my whole life. Thank you, Mom. And this is this month's National Geographic. I took a picture of the cover. It says, "This baby will live to be 120 years old." Well, genomic medicine is the mechanism by which we will live to be that age. So I have to ask you in closing, with this in mind, what I've showed you, how well do you know yourself? If you were prescribed a drug, did your doctor use genomics to help inform you whether that drug would be effective or even safe for you to take? Do you want to live to be 120 years old? Thank you.